Okay, so let's get to it then. We were talking about at the very bottom of the first page here that if the function is only defined up to some endpoint, like the square root of x, for example, then just replace the limit definition with the appropriate one-sided limit. So basically, just use your head. Okay. Okay. So I think what we actually ended with last time was the Mathematica demonstration. Okay. So what we concluded was, so let me regraph that function, and I'll just do it here in Wolfram Alpha so I don't have to switch devices. All right, so what was it? E to the minus x. That's not what I wanted. You go away. Ah, they've changed everything on me. E to the, where is all the, oh, e to the minus x, and then what was it, minus x? No, I don't want blast. Minus x, okay, I don't know what the heck I've done to the keyboard here. Okay, so here's the graph, and what did we notice? If we plug 0 into this thing, what kind of number did we get? I don't remember the exact decimal approximation, but it was a positive number, right? What did we get when we plugged 1 into it? Some sort of negative number, okay? And if I can't zoom in on this, but if here between 0 and 1, does that tell us that this thing has to cross somewhere between 0 and 1? Okay. But what's the one extra piece of information we need to know about that graph? Okay. Now it's obvious looking at it. Okay. But what, before I graphed it, did we know that the curve was going to be a continuous one? Okay. But perhaps should we have? Okay. Is x a continuous function? Yeah, should be. That one's really easy. What about e to the x? Yeah. Okay. What happens, do you think, if you add two continuous functions together? Do you think the result should be continuous? Probably so. Right. Okay. So, we should have guessed before we graphed it that this function was in fact continuous. Okay. And so it's not enough the fact that f of 0 is positive and f of 1 is negative. Because what about if the function were discontinuous? Does that guarantee that we're going to cross somewhere in between? Maybe, maybe not. So it's really the two things together. The fact it's positive in one end and negative on the other, and that it's continuous in between. Those two things together is what allows us to apply the intermediate value theorem. Okay, does that make sense? Okay, so let's write out formally what the intermediate value theorem is. And let me just start a new page here. So what's today, the 11th? Okay, so IVT for short, intermediate value theorem. Okay, so suppose f is continuous on some closed interval AB, and that f of A is not equal to f of B. So it's different at either end. Okay. Let C be any number actually, hold on. I'm not going to use C for this. Let me use D. Because I want to use C for something else. Okay, so a bunch of words, right? So we need to have a function that's continuous on the interval of our that we're interested in, and that interval is going to be from A to B, whatever A and whatever B are. Okay. In the example we just did, it was 0 and 1, but of course it doesn't have to be those numbers, just whatever it is. Okay. And we also need to have that f of A and f of B are different. Okay. They were different in the previous example, and we knew that because one was positive, the other was negative. Okay, but they don't have to be positive and negative. They just have to be different from each other. So pick a number that's any number that's in between those two things. If f of A and f of B are different, there's got to be something in between them, right? Probably a whole lot of different things in between them. Pick any of those numbers. Okay, then there has to be a value somewhere in between A and B so that the value of the function at that point, so f of c, f of little c, is equal to the number that you chose that was in between f of A and f of B. Okay. Now, does that make any sense? Yeah, go ahead. Sure. Mm-hmm. Okay, let me pull it up because your numbers may have been different. And all right, so hold on one second. Edfinity and Canvas. All right, so let me pull up the video too. Oh, and get through the stupid ad. Okay, so which problem was it? The second one. Okay. So let me scroll to that point in the video just to make sure I've got the details straight here. Okay, good question. Um, so there's maybe a couple ways to answer this, right? Is it possible or is it guaranteed? It's totally possible. Is it guaranteed? No. Okay, why? Okay, so in this one, f of 0, or sorry, f of minus 2 was 0, and f of 2 was 10. So our interval is from minus 2 to 2, and our y values are 0 up to 10. Okay, so is it possible that somewhere on the inside of that interval, the function hits 12? Yeah. We don't know any more about the function, so we can't rule it out. But is it guaranteed to happen? And why not? What broke here? Why doesn't the IVT guarantee it? Uh, that's not why. That's true that the function is continuous, but what? Bingo. 12 is not between 0 and 10. Okay. So had it been 8, say, that was the given value, then yeah, 100% guaranteed. But 12 or anything bigger than 10 or less than 0 is not guaranteed to happen. Because, for example, I could just draw a straight line. The function's continuous. Yeah, that was given though, right? Um, so the function is continuous on that interval, right? Okay, so the question is, does there exist a value C in between -2 and 2 where f of C equals 12? Is it possible? Sure. Is it guaranteed? No. Okay, does that kind of make sense? Yeah. This, by the way, is why we have to require that this condition, that the two values have to be different. Because if they're the same, what's the only value in between them? That common value. And so this really doesn't say a whole hell of a lot. Okay. Now, it could be that one end is bigger than the other or vice versa, right? That doesn't matter. They just have to be different numbers. Okay. Okay. Yeah, does that make sense? Yeah. So the function being continuous, like the IVT does not say whether a function is or is not continuous. It's assumed when you start it that it is. Okay. So if you have a function that is discontinuous, can you even talk about the intermediate value theorem? No, there's nothing to discuss, right? And because one of the hypotheses of the intermediate value theorem is not satisfied, okay, that namely that the function is continuous. Okay, so let me kind of give you an example here to illustrate why, if the hypothesis is not satisfied, you just don't care, right? Like you move on to some other discussion. So if I win the lottery this weekend, then I will give you each $1,000. Okay, seem like a reasonable trade. Maybe only the people that are actually made it to class today, right? Maybe the guys who skip get whoops, I skipped them. Okay, so we just made that assumption, right? So what happens on Monday if, as you guys are walking in, I'm handing stacks of Benjamins to everybody? What can you conclude? Absolutely nothing, right? Would you guess that, hey, maybe he actually did win the lottery? Okay, but is it guaranteed that I won the lottery? No. Maybe I'm just rich. Maybe I just like you guys. Maybe I'm selling, uh, you know, meth and coke out the back of my car, right? Yeah, I'm dealing in continuous functions during the week and dealing in coke on the weekends or something. I don't know, right? No, obviously I wouldn't be doing that, but yeah, like you can't assume or you don't know for certain that I had won the lottery. Okay. Now, on Monday, let's say that you come in and I don't hand you guys all stacks of cash. What can you conclude then? I definitely didn't play the lottery. Okay. Um, yeah. Now, so if the assumption is false, okay, if I win the lottery, so if I have not won the lottery, and which won't happen because I don't play the lottery because I'm a mathematician and I'm not stupid, and lotteries are taxes on people who are bad at math. Okay. Um, Basically, that's the way I look at them. Um, so, uh, can you say anything about the conclusion as to whether or not I'm going to hand you guys all a bunch of money? No, like that it just doesn't apply. It's not relevant to the discussion anymore. Okay. So same thing here. If you've got a function that's not continuous on this given interval, the IVT, right, it's just there's nothing to say, right? You can't use it. Okay. Does that make sense? Oui? No. Très bien? Okay, d'accord. Okay, so this statement here, in terms of the example that we were just working with this e to the minus x thing, what are the numbers little a, little b, little c, and big D? What's little a and little b for the example that we just worked? 0 to 1, right? Little a was 0, little b was 1. What is big D? Oh, okay, sorry. 0. So sorry, I meant I have kind of confused you. I meant this example, right? Not the one from the warm up. Okay. So in this example, right? What was our interval? A to B. Little a was 0, little b was 1. What was the value that was in between f of 0 and f of 1 that we chose? We chose 0, okay? And we know that 0 is in between there because one end was positive, the other's negative, so 0 is definitely in between those two things, whatever they are, okay? And so our big D, in terms of the way I wrote it, or big C on the sheet, it's kind of the same thing, is the number 0. Now, what about the number little c? It's whatever this x value is right there. Do I know what its value is? Like, I know it's between 0 and 1, but do I know like it's 2 or 0.73 blah 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 or anything else? No, I don't know what it actually is yet. I just know it's somewhere in between 0 and 1. Okay? So is that all right? All right. Now, so the IVT is an example of what we call an existence theorem. And this is maybe a little irritating to a lot of you guys. Because it says, hey, there is a number between 0 and 1 that satisfies this property. Does it tell you where between 0 and 1 it is? Nope, that's your problem. Okay. Now, why would we want to know if a given function is equal to 0? Well, we do that kind of thing a whole heck of a lot in math, right? We want to know where roots of functions are, right? So trying to find a solution to e to the minus x equals 0, like, we need to be answering these kinds of questions all the time. The IVT tells us that there is an answer to be found. Okay, it just doesn't tell us where the answer is, other than it's between 0 and 1. Okay, so think of the IVT as the mathematical equivalent of there be gold and then there hills. Okay, yeah. Or, I don't know, any Star Trek Voyager fans in the room? How about there's coffee in that nebula? No? Oh, you guys are pathetic. Okay, so it doesn't tell you exactly where the thing is. You have to use other tools in order to find it. Okay, and so that's sort of the next part of the discussion. Okay, so let's use the exact same function, e to the minus x. Okay, now we have just established that there is a solution somewhere in between 0 and 1, right? And from the graph, where does it sort of, roughly speaking, seem to be? I mean, this isn't the best graph ever, but what would you guys guess? Yeah, somewhere in the half-ish, 0.6, kind of somewhere in that ballpark. Okay. All right. So what we can do to try and squeeze in on it is, what about if we change our interval? Okay. So what was the interval that we were working with so far? It was from 0 to 1. Well, what about if we go between 0 and 0.5 and see whether or not it has to be between there, or between 0.5 and 1, right? So we start to split the interval in half and look at each piece separately. Okay, seem like a reasonable idea? Okay, and we could keep this game going all day long, basically, until you get it as precise as you want. But let me actually go over to Desmos because it'll be easier to see, I think, with the graph there. So let's see, Desmos. Here. Okay, so what was it? E to the where's the E? Okay, here we go. E to the, oops, not that one. Blast. E to the negative x whole thing minus x. Okay, good. Okay, so let me sort of zoom in on this thing. Okay, all right, and now that we've zoomed in a little bit, what do we know is going on? I mean, obviously from the graph, it's between 0.5 and 1, okay? But how would we know this without a graph, right? What happens if I plug 0.5 into this function? What kind of number do I get? It's positive, okay? What about if I plug, well, we already know what happens if I plug 1 and I get a negative, right? So is there guaranteed to be a root somewhere between 0.5 and 1? Yeah, okay, so let's squeeze in a little bit. What about if we did like 0.5 to 0.75? Would that kind of squeeze it in, right? So if we kind of squeeze in our interval, and we say, okay, well, let me try between 0.5 and 0.6. Does it work? Yeah, okay. So what about between 0.55 and well, just keep going. 0.55 and 0.58 or something, right? Now, is this a really efficient method of doing this? No, okay. But it does kind of give us a ballpark estimate that, yep, there's a root there to be found, right? Now, there are other methods of actually finding this root that are a heck of a lot more efficient, okay? In fact, the most primitive one actually uses calculus, and we'll talk about that one later in the semester. Okay, it's called Newton's method. Okay, but does the idea kind of make sense? Yeah. All right, now, let me go back to Wolfram Alpha for just a moment because it calculated a value that, or approximated a value that's the root, and it did so using some of these sort of sophisticated techniques. And with those sophisticated techniques, what you first have to do is have a guess. What's our guess? Is it's not perfect, but 0.5 seemed pretty close to the correct answer. So we use that as an initial guess, and then we keep making the guess better. Like I said, we'll talk about that method later. And we get to a whole bunch of decimal digits here, 0.4, 5, 6, 7, blah, 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 blah. Okay. So the theorem guaranteed it was there to be found, and then we used a different thing to find it. And if you guys will permit me to stick with our gold finding analogy, the IVT is like the metal detector that beeps. Then you still got to get out the shovel. Okay. Huh? Right. There are situations where the metal detector doesn't work, right? So, yeah. I mean, it's not a perfect analogy, but, when are analogies ever perfect? Yeah, like never. So, okay. So, make sense? Yeah? We know. All right. So, let's flip over here to the back page. And what I'd like you guys to do is just we'll split you, work with a buddy. Okay, 6. You two will be 7, 6, 7, 6. You two will be 7, 6, and 7. Okay. Huh? On the back page. Are you looking at the right sheet? How about the one on continuity? Yeah, that one. Okay, so take a minute and think about your appointed problem, and then one person from the number 6 group write up the argument on the board someplace, and one person from the number 7 group write it up, okay? All right, so does it make sense kind of what the question is? Yeah? Okay, so you want to show that there are, that these two equations have solutions, okay, under certain circumstances. The ones with number 7, who's got number 7? What's missing? That means you got to figure out an interval. Which means using your noodle. Right? So you got to figure out an interval to work with first, and then maybe that'll help. So I just looked. It doesn't look like Nuevo Kentucky Cafe still exists. But I was able to find its menu and its address, and then I just Google Maps to the appropriate address in Tijuana, and it definitely is not that anymore. So, and it looks like all the buildings got torn down and replaced with stuff. So, oh well. Yeah, question or pregunta? Well, okay. So, what's the function is that thing, right? All right. So, what's f of zero? Zero, right? So here our function is the thing on the left, right? Uh, f of 2 is what? Is 3 in between those two numbers?
Yeah, so is that basically what it's asking?
Right.
Okay, so I can set would I state that since it's continuous?
Since the function is continuous on the interval from 0 to 2, and
It's in between.
3 is in between 0 and 80, therefore, by the IVT, a thing exists somewhere between 0 and 2. Now, where between 0 and 2? Got me, but it's somewhere there. Yeah.
So how do you find an interval working?
Yeah, okay, so this is tricky, right? Um, because you can't cheat, right? Now, and you're not psychic either. So 2 to the x is always a positive quantity, correct?
Yeah.
Yeah, okay. 3 minus 2x, definitely not always positive. Okay. Um, so at this point, you want to show that a solution just exists, okay? So my suggestion is, what about if you move all the pieces to one side so that you're saying, is something equal to 0? That might be a little easier to get your hands on. Right, because just move everything to one side. Okay, now, if we're looking for where something is equal to 0, then from the previous example, we know that what we want is an interval so that on one end it's positive and on the other end it's negative. So then let's just try picking some x's and see if we can find an interval where if we plug in a number, we get a positive in one place and a negative in another.
So one, so 2 times 1, or 2 to the first power is 2 plus
Mm-hmm.
2 times 1 is 2, 4 minus 3 is 1.
Okay, so at 1, the function's positive. What about if you plugged in 0?
Okay, so maybe 0.5.
Well, just plug in 0. One.
Yeah, maybe.
Oh, well, there you go. You found an interval where it switches sign. Okay. Now, is that the only interval that could have worked? Maybe, maybe not. Okay, because two things are true. Like, what about if the graph does this kind of thing so that it crosses the axis a whole bunch of times? Well, there might be other solutions out there that we just haven't stumbled on.
And we don't know how many solutions because it's to the x power.
Well,
We don't know how
let me
many
just say
axes.
we have no idea how many solutions it has, but we do know it has at least one,
Right.
and it's somewhere in that value. Okay. Now, we could squeeze in on it, kind of like with the same argument we did a minute ago, right? What about now if we try plugging in 0.5? What do we get? Well, so this is a little harder because do you know what 2 to the 0.5 is?
It'd just be calculator for.
Well, okay, so you could use a calculator. Another way to do it is 2 to the 0.5 is really square root of 2, right? Which is like 1.414-ish. And so we could kind of estimate 1.414 minus, or sorry, plus 2.8 blah, 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 minus 3. Are we going to be plus or minus? Definitely plus. Okay. So what that means is um, it's somewhere between 1/2 and 0, right?
Mhm.
So we've squeezed in and cut the interval in half.
And I'm guessing we're going to learn here a few minutes how to do something like more efficiently.
No, we need extra tools first. We need the derivative before we can do it.
Oh, I forgot.
Yeah, yeah. So yeah, so there's a better solution. Like I said, the IVT only guarantees that there's a solution out there to be found. It doesn't tell you anything about how to find it. That other method is stuff we'll deal with later. Okay, but we need more tools first. So, yeah, why don't you guys put that one on the board? Who was the number 6 group? All right. Why don't you guys put it up over yonder? Okay. What are you? Sure.
Right. So pretty much what you do to solve these, right, is you take 3 over to this side and you set it equal to f of x. Or is that...
You could,
Okay.
or you could just make f the stuff on the left and say, all right, if that's f, what's f of 0? 0.
Okay. Yeah.
What's f of 2? 80.
Yeah.
Is 3 between 0 and 80?
Yeah.
Last time I checked, yeah.
Yeah.
So you can define the function here to be just the stuff on the left, or as I think you'll see with what they're going to do, move everything to one side. The difference is if you move everything to one side, you're trying to find when your function equals 0. Whereas if you don't, you're trying to find when that function equals 3. 6 of one, half a dozen of another.
Gotcha.
Right?
Okay.
But often, I think, for a couple reasons, it's easier to work with if you're just setting things equal to 0 in solving, because then you've got the whole plus minus thing at your disposal, right? Because sometimes you can stare at something and it'd be like, I have no idea what number I'm going to get if I plug in, but I know for damn sure it's positive or whatever, right? So that just kind of from a practical standpoint is slightly easier to work with. Yeah. So. Yes. You can or you can't, right? That's actually up to you. Okay, and in fact, you guys did move it. Why don't you guys write your version up over there? Okay. Okay, because the details will look slightly different, but the conclusion will be the same. Okay. Okay. So we got plenty of time, so we'll wait until they finish writing them up, and then we'll discuss. And Mark, where did Dude Bro go? Well, I probably am guessing where he is right now, but let's just say he's probably also producing roots. We're making fun of you, Jeremy. Yeah. So, okay, we're good. So, actually, don't back over there because you get to explain yourself. All right. So, what did you do? The given interval was 0 to 2. So, what did you do with 0? Oh, and for that matter, right up above f of 0, what is f of x? Right. And the reason and Arthur, same thing, right? What your f of x was over the your function. And because it's important, because they use different functions. In just a second, yeah. Let Arthur finish scribbling and then. Okay, so go ahead. And that one's easy and obvious that you got 0, right? Okay. because 3 is between 0 and 80. Yes? Okay. Now, then the last thing is, how do we know that that function is continuous? It is, but how do we know that just immediately looking at it? What kind of function is it? It's a polynomial. Every polynomial is continuous. Okay, so, right. But we need to make sure that it is. Okay, all right. Arthur, what's y'all's variation on this? Yeah, so theirs was slightly different, even though the result is the same. By moving the 3 over, they're looking for where their function is equal to 0 rather than where it's equal to 3. Essentially, their picture is just shifted down 3 units from the other version. Okay, but it's the same question, basically, right? Now, the possible advantage, you don't necessarily have to do this, but the possible advantage of moving everything to one side so that you're dealing with equals 0 is because that might make the arithmetic a little easier, because then you've got plus and minus that you can think about, rather than over with the other version, you'd have to think about bigger than or smaller than 3. And maybe it's easier to think of positive and negative. Both versions are perfectly correct. Okay, so some of this can just be a convenience thing. Okay, good. All right, what about number 7, which is over here? So
we had equation 2, the x equals 3 minus 2x, so we put them all together on the same side to set it equal to 0, and then we plugged in different values. First, we start with 1, and we plug it in, and you get positive numbers, and you plug in 0, and you get negative numbers. So our initial range was 0 to 1, and then we kept going by plugging in 1/2, and we found out that 1/2 equals 0 to 1/2, because 1/2 is also positive.
yeah, so the difference between this one and the previous one is they didn't have an interval that they started with. Okay, so notice the statement of the question in number 7 is just show that this equation has a solution. Okay, someplace, a real number somewhere. Okay, so if you don't have an interval given, you have to come up with the interval. Okay, and now, are we going to be jerk faces and make it like that the solution is somewhere between x equals 193 and 420? Of course not, right? Like, no. I mean, could it be theoretically out there? Yeah, but like, am I going to deliberately construct a question with that crazy property? Probably not, okay, because I'm not trying to trick you guys. But the point, though, is that you don't know the interval, and so you have to just start testing some values until you see, hey, it's plus here and it's minus there. Probably gonna, and is this function continuous? Yeah, definitely. And so it will work out, okay? Yeah, so if the interval is not given, start plugging in a couple of numbers just to kind of get a sense for it. This is one reason where, of course, this being the 21st century, right? We all carry gadgets in our pockets that can graph this thing like in 10 seconds, right? In fact, it probably takes you longer to get the thing out of your pocket and have Face ID, like lower your mask so that the Face ID works or whatever before you can get into Desmo or what to graph it, right? Um, yeah. So anyway, is that cool? It's cool, cat. It's cool. Okay. So let's look at the last two here. So we got a couple of true or false questions. Now, you guys have been in other classes. Do you like true or false questions on quizzes or exams? You do? The answer should be no, they are the worst things ever, okay, because they're technical. All right. So let's think about this. Let's suppose that we have a function that's continuous on the interval from 2 to 4, and at one end it's equal to 2, and at the other end it's equal to 4. Then the function's value is between 2 and 4 for all x in that interval. True or false? Who votes true? Who votes false? Okay, now here's the thing. If you think it's true, you have to prove that that can happen. If you think it's false, all you have to do is draw one graph that demonstrates that it's false. Okay, so let me sort of rephrase this a little bit. If I say the following theorem, all horses are spotted, okay, how would I have to prove that statement? That would be how I would disprove the statement, right? Is so if you walked in with a, beautiful brown horse that has no spots on it, then you have just disproved my statement. It just takes one counterexample. For me to prove that, I would have to literally march every single horse on the entire planet past a podium and be like, yep, spotted, yep, spotted, yep, spotted. Okay, keep going, and next horse, next horse, next horse, until we hit the end of all the horses on the planet. Okay, now that's sort of a ridiculous example, right? But point being that it is a lot easier to disprove something than it is to prove something. You just have to find one example that breaks it. There could be 50,000 examples that break it, but you just got to produce one. All right, so Jaden, you think it's false. Would you please draw upon one of the chalkboards a function that satisfies the hypotheses but does not give you the conclusion that was desired? Okay. And make sure you label A and B, right? Okay, so f of A was supposed to be 2 and f of B was supposed to be 4. Okay. Yeah. So what is f of A here? 2, that was given. What is f of B? Does his function satisfy that that's equal to 4? Yeah. Is the function always between 2 and 4? Nope. Because he made it go up to 6 and then back down to 4. Does that work? Yeah. Okay. Is it possible that there's a function that satisfies this property? So is there a function that never gets bigger than 2 or less than 4 on the given interval? What would that one look like? Well, for example, just connect the 2 points with a straight line. That would do it. Okay. But so just because there is a function that satisfies that property doesn't mean it's true for all of them. Okay, so what's the conclusion for part A here? True or false? False. Okay, so Mark, you're fired. Sorry. All right. Let's suppose the second one. F is continuous on an interval, and somewhere in between the function is equal to 0. Okay, seems reasonable enough, right? Then f of A and f of B have different signs. What's your gut say before you start thinking about it? True or false? Who votes true? Who votes false? Who has no idea? Okay, that's all right. Patrick, you voted false. Why did you vote false? Okay, could you draw me an example graph that satisfies the hypotheses but does not satisfy the conclusion? Yeah. Okay, so he's going to draw his example. Then I'll draw a second example, which is going to be super cheapskate, right? Super dirty. Does that satisfy the hypotheses? No, right. Okay, that works, right? Well, okay, actually, that doesn't quite work because, let me doctor it up slightly. The value where it hits 0 has to be in between A and B, but not at either end because of the inequality. So I could have something like that, right? Does that 0 somewhere in between A and B? Are f of A and f of B of different signs? Nope. Okay. Actually, my cheapskate solution would just be the function equals 0. Because what's f of, if 0 and 0 are those two values, do they have different signs? No, because 0 is neither positive nor negative. Okay, that's a cheapskate one, but yeah. Okay, yes?
But it says it's less than, it's not less than or equal to. Could that have to change? But it can't just be the function equals 0.
No, the function still equals 0. So the less than is just that the value, the place where it hits 0 that's given must be between A and B. It doesn't mean that there can't be other ones too. Okay, so, all right, so it's 8:50, so a couple of quick points. I'll have your assessment thingies for you Monday. I'll post a bunch of new stuff to Canvas. Sorry about the mix-up on the warm-up dates. Hopefully you guys all saw that announcement. And if anything like that ever happens where I screw up and things aren't matching, just please let me know, because it's easy to make those mistakes. So, all right, have a great weekend. Don't get arrested. I hear there's a raging party at some place.